In this video, we will take a look at some example problems of working with Le Chatelier's principle. So looking at different stresses and determining how is our equilibrium going to shift and how is that going to alter our concentrations. So if you look at problem number 3, we're asked how will the following changes alter the hydrogen concentration in the following reaction. So we've got iron reacting with water, producing iron for oxide and hydrogen. And so the first thing we're asked is about removing water. So if we look at our equation, if we're removing water, water is a reactant. So remember, if we're going to remove something, our equilibrium is going to shift to replace what we removed. So if we removed a reactant, we have to shift towards the reactants to replace it. So our equilibrium shifts in the reverse direction. The result of that is it's going to produce more reactants, and it's going to use products. So this question is asking us specifically about what's happening to hydrogen. So hydrogen's a product. We just said we're going to shift towards the reactant, so we're going to use products. So we're going to find that the hydrogen's concentration would decrease by removing water. Now next we're asked about iron oxide. Now the iron oxide here is, first of all, it's a product, but the other thing we've got to recognize is that it's a solid. So remember that our solids do not impact our equilibrium. Changing a solid is not going to shift our equilibrium. And so since that iron oxide is a solid and there's no impact, we're going to see no change in our hydrogen concentration. So hydrogen stays the same. Now next we're asked about increasing volume. Anytime we change volume or pressure, we've got to look at our number of moles. And in particular, we've got to look at our number of gas moles. So looking at our reactant side, my iron is a solid, so it's not going to impact anything. My water here is a gas. And so I have 4 moles in my reactants. So then looking at my products, on the product side I've got the iron oxide and the hydrogen. The iron oxide's a solid, so we're not worried about that. And then I have the hydrogen gas. Its coefficient is 4, so I have 4 moles of product. So in this scenario, my reactant moles equal my product moles. And if the reactants and products are equal, then we can change pressure and volume all we want. We're not going to get a shift in that equilibrium. It's not going to alter our concentrations. So we're going to find no change. And so my hydrogen stays the same. Now next we're asked about an increase in temperature. When we're talking about the impact of a temperature, we always need to look at our energy change. So our delta E or delta H, depending on how they quote it to us. And so we need to know, is that reaction endothermic or exothermic? I have a negative delta E, so this is an exothermic reaction. For an exothermic reaction, if I'm increasing temperature, remember that exothermic, we are releasing heat. So heat is a product. Increasing the temperature is the same as increasing a product. So if we add product, remember anytime we add something, we shift away from what we added. So we have to shift away from the products. So it shifts in the reverse. So if my reaction is shifting in the reverse, again, we're making reactants, we're using products, and we would find that the hydrogen concentration decreases. Next, we're asked about increasing pressure. We already talked about changing volume. If we change volume and pressure, it's all dependent on those moles. So remember, my reactant moles equal my product moles here. And since they are equal, we're going to see no change. So in terms of my hydrogen concentration, hydrogen is going to stay the same. And then finally, we're asked about a catalyst. When we talk about catalysts, again, their role is to change our mechanism, to speed our reaction up, but they don't alter concentrations. We could add a catalyst at equilibrium, and we would see no change. Now moving on to our next problem. We've got this reaction of nitrogen monoxide gas with chlorine gas to produce 2ClNO. And we're asked if the pressure of the reaction container decreased, so pressure decreased, we want to know what will happen to the concentration of the chlorine. So if we're talking again about pressure or volume changes, we've got to look at our moles. So looking at my reactant side, I have 2NO plus 1Cl2. So that gives me 3 moles of reactants. On my product side, I have the ClNO. Its coefficient is 2, so I have 2 moles of products. The reactants and products are not equal. Since they are not equal, changing the pressure or volume will impact this equilibrium. So here we are decreasing pressure. If we decrease pressure, remember my equilibrium is going to try, or my reaction is going to try to bring that pressure back up, and we get greater pressure by having more moles. So decreasing the pressure will cause my equilibrium to shift toward the side with more moles. So my reactant side has 3 moles, my product side has 2. The side with the most moles is the reactant side. So it's going to shift in the reverse direction. Now we're looking to see what happens to the chlorine. If we're shifting in the reverse direction, we're making more reactants. Chlorine's a reactant. So we're going to find that the chlorine concentration increases. Then we're asked about increasing the temperature. So again, that depends on if our reaction's endo or exothermic. I have a negative delta E, so this is an exothermic reaction. In an exothermic reaction, increasing temperature is the same as increasing the amount of a product. If we add product, we're going to shift away from it. So it's going to shift in the reverse. If we were still asking about chlorine, it's going to increase chlorine's concentration. Now our final problem here. This is an example of a problem that takes place in your body. This is the metabolism of sugar or glucose, where we have C6H12O6 reacting with oxygen, producing carbon dioxide and water. So we're asked how the following changes are going to alter the carbon dioxide concentration. So if we were to remove oxygen, we're removing a reactant. We shift to replace what we remove. So we've got to shift towards the oxygen. So it shifts in the reverse. If we're shifting in the reverse, we're making more reactant. We are using product. So the carbon dioxide goes down. If we were to remove some glucose, that glucose is a solid here, so we're going to have no change. If we were to decrease volume, we've got to look at our gas moles. On the reactant side, I have 6. On the product, I have 6 CO2 plus 6 water. So I have 12 moles in my products. They're not equal. decreasing the volume, it is the same as increasing the pressure. So we said if we increase the pressure, we're going to shift to the side with fewer moles. My side with the fewer moles is my reactants. So it shifts in the reverse. So we're making reactant, we're using product, so my carbon dioxide concentration goes down. If we were to decrease temperature, so again, we need to know endo or exothermic. This is an exothermic reaction. Remember, it's metabolism. This is how your body gets energy. We want that energy to be the product of that metabolism reaction. If we decrease temperature, this is the same as removing a product. We're going to shift towards what we removed. So we shift in the forward direction. Means we're going to make more product. So our carbon dioxide concentration increases. And then finally, if we add a catalyst, again with our catalysts, they do not alter our equilibrium. So we would see no change.